Thank you very much. Thank you very much. I'm very happy to be here. So today my talk will be about the TimescaleDB jam, and yeah, this is my work at Timescale, and this is a introduction. I guess I made this type of introduction a few times, but I compiled the slides yesterday, so it's 8 slides, and I will maybe break the flow at some point because I need them to remember where I am. And my name is Jônatas. I came from Brazil. This is my fourth time here. I spoke at Ruby Conf KRUG, Ruby Crackle in 2019. And it was very nice to be here my first time. I went here also for Lambda Days 2 years, so I love Lambda Days. It's a very nice event here. And I love functional programming. I'm not a functional developer, but when I go there, I pretend to be. So, and I am a developer advocate and also a community manager at Timescale. So I split my time between these two areas, and our community is very large. We have like more than 12,000 people on our Slack, and we have presence in several other types of networking. And so part of my work is answer you at Stack Overflow or whatever has questions online. So that's part of my work. So as I work a lot in the community, this is the talk that I thought like, if I could bring something for Rubists, I would show this type of thing. And the workshop I will have tomorrow is all my like 4 years working at Timescale knowledge, and I will be speaking a bit of it today. But today I will be walking through the TimescaleDB features and show you how you can write the Ruby code that makes it work, right? So this is the repo. If anyone would like to check, this is TimescaleDB/Ruby, and this repo is basically it was my private property until this year. So I was doing this inside the company, and the company basically they just say that. Ruby folks don't build like a scalable system, so they say like, why are you fucking doing this? And then I was like, okay, I need to stop doing the work, and then I continue doing this at my free time. Really nice. And then this year, this CTO just come to me and say, why this amazing project is in your personal workspace? And then like we moved this now to the company workspace, but it was my work in my private rep for quite a while. It was not private, sorry. And basically the setup is, as everybody knows, it's just a TimescaleDB. And for those that are not familiar, TimescaleDB is a Postgres extension. So you do bundle install, but it will also depend on you have it on your Postgres install. So Timescale as a company works on several extensions for the Postgres ecosystem. So TimescaleDB extension is responsible for time series data, and this is the, let's say, first concept that I will show you. That's the hypertable. So we added the migrations hypertable keyword that you can, let's say, plug out timescale features when you are creating your table. So on the timescale side, hypertable is like an abstract concept of partitions. So when you say create hypertable, it's basically setting up some options. Here are the full options. So what you are doing is saying like, hey, here is the created at column of my table. Split the data per month or split it for a year. So you have small, let's say, partitions, and every partition maintains its own metadata. So like Postgres is very good. It's made to run in a refrigerator, so it's made to run in a very lightweight hardware. And when you get Postgres with more than 100 million rows in a single table, you see that some performance gaps start happening. And that's why partition works so well. So if you put partition, you basically you have several tables, and you will try to not to fetch them all at the same time, and that will be a same process for your work. So uh, and the cool part of having partitions and knowing that some data belongs to a specific point in time is that you can start recycling the data. So we have this idea of compression, like old data I can compress, and if this is very old, I can even delete the data. And for those that don't know, like deletes in Postgres, there is no delete. There is just a way that you mark your tuples to be hidden, and then like there is some vacuum work that needs to be done there, and this vacuum can be very expensive. And this is why this partition matters. So when you have partitions, then you can drop the entire partitions, and it says like partitions, indices, and all types of things will just have gone together. So it makes your Postgres much more healthy in general. And here is a very small example of the model. So and this can be let's say translated into SQL. So I'm going to show you now the hierarchical continuous aggregates. So we call continuous aggregates this idea of more smart materialized views. And then you come for raw data, and then when you have the raw data aggregated like in a minute base, you may think that you can do it, roll out it for an hour or for some day, and then the hierarchical views can help on this. I will be digging very deep on this. This is a pull request that is open on Ruby Gems. We are adding it to TimescaleDB to be tracking the downloads statistics now. So it was a work that was started by Samuel, the guy that we will speak later here. And he couldn't finish it, so I was like, it's a great use case for my gem. I need to make it happen, and I need to learn and discover. So most part of the macros and things I'm doing now is very, let's say, oriented to the work I'm doing in the Ruby gems to try to make it more easy to use, because in the end, when you become a user of the technology, you know that it's not that easy. So that was my point. And it was really cool. Basically, like this is the default syntax for creating a continuous aggregates. And you can do it by hand, like you just build a query and say that it's a continuous aggregate. And then you can also add this aggregation policy. So I will be going more deep into like how the policy works. And the policies are very good because in the end as a Rails developer in the past, I remember starting a lot of and working on a lot of like sidekick jobs that was just doing this type of thing. Like, hey, I need to refresh this, I need to recompute that thing. And moving this to SQL is very cool because when you move things to SQL, think that your database generally it's IO bound. So you have some free CPU in the database. Generally, the database bottleneck is the IO. So why not use this idleness time? So TimescaleDB introduces a background job system inside the database, so you can schedule things, and this is the interface is open. You can put your custom jobs, but you can also put, let's say, continuous aggregates refresh as a policy there. So it's very cool and very easy to use. Like add the continuous aggregates policy there. For example, I can be refreshing a table and doing this type of things, and it's very easy to go. But when I was working on the Ruby gems, I was feeling it was too much code, it was too much things, and I was like, I need to have a single line. This is the single line, still 20 lines, but this is the closest they got. And basically, in this case, I create a macro to start reusing the scopes and build the aggregation from this syntax. So the problem is that generally you have like a statistic in 1 minute, but you will roll out it for a day or for hour or month. And then when you roll out, it's like all boilerplate code. So I was trying to bring these macros to also make it easy and like set up more different views in a easy way. So in this case, for example, you have like continuous aggregates count clicks. So you have count clicks per minute, you have count clicks per hour, per day, and so on. And then it will generate the 12 materialized views, and also, 9 materialized views. And the 9 materialized views are also like inherited by the previous view. So it's a kind of boring work that you need to do. And for the migration, you just say create continuous aggregates, and it incorporates what you have in the macro. But basically, to generate all of these sequels. So yeah, if you go here, you can see, for example, count clicks per hour, and then you can see how it works, and that's about it. So I would like to go into this hierarchical part that is very interesting, and a bit of how we see like data lifecycle in general. And so the first thing on hierarchical things is like the interval you are going to use and how much granularity you really need. So generally speaking about the density of time series data, you think about like hour, minutes, day, weeks, and so on. And then you start to like having different intervals. Like if I have like hour data, for example, I can like leave this data for much longer time, and so on. So this generally we see this is very cool because it's very rare that you need to go back to the raw data. In case you need to store it for long term. We also have functions that allow you to move, for example, move chunks to cheaper storage, so you can build another workspace inside your Postgres and move data there too. It's also fun and also a very good one. And the cool part is that it controls the refreshes for you. So think about like, let's say you are building an IoT system or whatever, and then you need to have a backfill, like you have data from 3 hours ago coming, and you need to refresh. But then you refresh the minutes, and then you refresh the hour, and then you need to refresh the day. And this kind of dependency chain of how you refresh will depend on like what is already materialized, what's not. So the watermark just controls where the last refresh stops, and it allows you to go back and forth with the place that you touched. And basically, I think that you always have this threshold that you can keep dragging, and then you will when you complete the job, you advance. For example, if I'm processing every minute, I will just advance 1 minute. And then knowing the watermark, the cool part is that we build a technology named real time. So you know where you stopped in the materialized, and then you can go to raw data and just get like these last minutes and have it like really real time. So it's embedded by default in the engine. So you just say materialize only or true or false, and it already goes and change all the queries behind the scenes and do all the witchcraft to make it work. So this is a good thing because database is supposed to be consistent. So if you make this system consistent, it controls all these abstract refreshes that you need to do. And seriously, it's very boring. Who wants to keep managing it for all the new tables, right? So this is a very, very useful. And together with this technology of watermarks, we have another system that's invalidation logs. So think if you touch some data, instead of inserting data, you touch the update something. So you can keep the track of the parts of the past data that's invalidating. So the next refresh, it will also collect these small pieces that need to be refreshed and refresh them in parallel. So it's very, very useful. And yeah, the materialized only strategy I already talked here. That's the problem of my slides. And I also want to share a bit of toolkit. So basically, we got into a point that the statistics on Postgres were not really performant. And then we end up creating a new extension named the TimescaleDB toolkit. That's like a pandas for SQL. And it has even a functional programming pipeline inside SQL that you can do pipe operators and do very cool stuff. And this project, it has like 150 different statistics functions until now. And basically, we build mathematical components that allow you to create like mathematical sketches. So the first one is this what we call stats egg. So this is a pure SQL just to show the concept. So imagine that you are tracking values and you want to extract several statistics from this aggregation function. Like stats is from statistics, so it means like average, standard deviation, all types of basic statistics that you get from a series of data. And then you can build it like 1 minute. So, and what you can do is, for example, if you go to 1 hour, you can roll up. So instead of having the final materialized values, you have this like, it's literally a struct of sketched data. So it has an arrays of some values that are important to recover to that calculus. So we have it for several types of components. And in this case, like you roll out, so you have this metadata that you can merge. It would be like a hash merge or some join, something like that between the objects. So you can keep rolling up mathematical sketches. And it also works with window functions. So you can keep the window open, and I don't know if who here is familiar with window functions on Postgres, just to check. Yeah, so imagine that the window is basically another level of your query that you can set up an extra slider that you can do extra things, like you want to rank your data or you want to do some something else. You can use a window function to have this extra way. And so these functions, we have a lot of them. So just to have it in mind, like statseg is accessing the value only in the most basic level that goes to raw data, and then in the other levels it goes up. And then we have a lot of functions like gauge, we have percentile aggregation, we have heartbeat aggregation, we have like status aggregation, like you want to check this, all types of things. So it all works, and yeah, I built most of the embeddings for these functions also in the Ruby library. I will not show them because it would be repetitive. And yeah, that's just the open parents of this toolkit extension. That's a cool stuff, yeah. And here is an example of a happy person just enabling compression, and going down for like 95% of your space. So it's really, really cool. And we see 95% is our default compression ratio in general. Like we see 90+% of compression ratio, and it's really, really good. And the thing is that generally, as I was sharing before, this idea of let's say idle CPU and I/O bound database. Compression will just use more CPU and use less I/O because you have a shorter reads in I/O, right? So in the end, it releases I/O and just uses better CPU. In several types of queries, it makes the query faster. especially on statistics and this type of thing. So it really makes things faster, and it's really good for it. And yeah, this 95% compression ratio is most of the thing. So it means that you have 5% of your storage, and it means that you can put like 20x more data. And the problem of the compression is generally because um, people get a lot more data than they could easily put. I will allow because I want to give up. Uh, Basically, when you enable compression, you create like a hash map of your data. So imagine, for example, in the case of this table, we are talking about events, and we have like identifier. So the identifier will just group events of the same type together, and then you can imagine that you can serialize this in another level. So let's go deep into this. So for adding, it's very simple. It's like add compression policy or remove compression policy. It's very easy. And we have, for example, imagine that you have this, let's say, a small partition of like 8 gigs, and then your partition just become 100 megabytes. And then you can merge multiple partitions to make it like a better size. You can segment by, but the cool part is how it applies the algorithms. So when you, oh sorry, I will talk about the algorithms in a minute. Basically, when you compress, you are compressing the entire partition. And what it do is like, it's already cold data. So the data is not being updated, so you can go and get the entire partition in a single compressed shot. So and it swaps the entire table. So it's very easy to drop the old table. Dropping a table costs nothing because it's just like removing the disk access to the file. It's just like echoing null in the file, and then it's over. And everything is aligned in the in the partition level. So, for example, you will not have indices. Most of the indices will be done by the strategy that you are using. Now, this is a bit outdated because they introduced some new levels of indexing inside compressed hypertables like last month, and I need to update this. But basically, most of the indices, they are the way that you query and you fold your data to then compress it. So here are a bit of the algorithm. So basically, we have this delta encoding, deltas of deltas, and a few other scenarios that will be applied. And then it tries to apply a few algorithms and then checks, for example, in some cases it applies the algorithm and check what works best, but it's not a dynamic thing. It's just like the chosen based on the first attempt to interact. So here's an example. So imagine that you have a table and you are receiving CPUs and memory and temperature, and then you are going to compress it. So the first step of compression would be grouping the data. Applying the delta, for example. So like in the CPU, you can see in the temperature. So and then instead of storing the value, it stores the delta. So generally, it's much smaller data, and then you can apply another shot and get the delta of the delta. So you just keep the value going smaller. And here's another example, like simple 8-bit. So instead of like putting all the sequence, you just put like how long it repeats, and it's also very fast and also very easy to decompose later, right? And for any text, it will use dictionary. So if you have like a binary JSON-B column or anything, it will become a dictionary, and it's also very, very fast and very easy to do. The only boring part is that we don't have any open functions to see the intermediate states of this compression. You just believe that it works, and I am always arguing you with the core team, like, can you open this API for us to just inspect these compressed objects? And yeah, we don't have a way to get these intermediate states. And yeah, this is really, really cool. And we also started a new thing because a lot of folks started compressing too early. And one challenge that Timescale is trying to do is at some point we want to enable compression by default. Everything just comes and becomes compressed. We couldn't make it yet. So it's too many exotic cases that if we enable, we can break with a lot of systems. So it's not that easy. And this is a new thing that we are building. So here's just another visual example to show the difference of like compressed versus decompressed. And you can understand one thing that's very important is we have a fixed let's say array size. So let's say, for example, your status code is an integer, and then you have an integer array that will represent exactly the same status code, but it will group, and the group is 1000. So it always group things in 1000. So if your table doesn't have like 1000 records of some specific type, you may not get like really good results because it's too little data to compress, right? And what we see here, for example, is like you put the compression, and then just now imagine that you have an update on this data. So how you handle this type of things, right? So it's very hard to make it. So generally, if you insert some data, like the last line of this table is like the new data, it will just create an array of one element inside, so it's very inefficient. But the key thing here on this architecture is like it marks the chunk to be recompressed. So this is another thing, like you mark like this is a dirt chunk, this needs to be recompressed, and then it will be done in another time. So it's just like to make things really smooth in production. Sometimes you need to batch data and just keep flagging things to later resolve it. And then with this idea, we create this, let's say, staging area. So this is like a clipboard memory that will always be like patched when you query something. So you query things, and then you also go to this extra memory and say, hey, let's see if we have any other transaction that we need to fix because this chunk is dirty. So that's a way to keep the acid into Postgres, but still not process things and still offer like fast and dynamic compression system. So it's a very complicated system to build, but it's cool because it's generic and works to any data. And then when you mark this to recompress, it starts understanding like the areas that you are touching the data, and decompress only the batches that are nearby your part to make it clean again. And then the staging area is empty again, right? So that's a very common question that a lot of people ask if compression ratio is too low. Generally, we have like if you come with a table like with thousands of columns or hundreds of columns, and if you may have like too many binary data or too many different exotic columns, so you may have like a very bad compression ratio. So generally, you need to see what's of your data can be compressed. Like this is really a good thing. So, and in some cases, you need to split your hypertable into multiple hypertables to just make, let's say, a reasonable series that you can reuse. And yeah, so data retention. This is how about controlling the size of your database. We have we you can add this retention policy. It's basically creating a background worker that will make it make this dropping the old chunks. And for example, let's say you have 1 month 1 month chunk, and then when the entire chunk becomes 6 months old, then it can drop the chunk, right? So that's the idea. So you keep dropping raw data and just maintaining the continuous aggregates data that you need. So here is a small example. So imagine that you have like 1 billion rows per day, right? So you have 100,000 devices, so you are collecting 108 billion rows in 6 months, right? So if you put like the retention policy of 1 day, then you just have 1 billion rows. And then like all this raw data will become controlled. And this is the point. Like for example, sometimes you can do something else. Like in our product, we have a cloud tool. We build a tiered storage that we move data to S3 to not to delete the raw data. So this is another. I will not cover it here, but basically this is a way that you can keep data. But some raw data, it will be so insane that you will not be able to keep it. And then that's the point. Like we have our dog food project. We are ingesting 800 billion rows per day, and that's very cool. We reached 1 petabyte and 400 terabytes already, and then just to think like about how the pipeline works. So in our case, the chunk time interval is 10 minutes. So every 10 minutes we have a new table, because after 100 million rows, it slows down. So you need to keep it in mind and think about like partitioning. And we also we couldn't build a system that could validate it. Like for example, oh, I would like to partition when I come to 100 million rows. This is not an easy problem to resolve. Just to say, like this is a very complex thing. You need to think that you need to keep dragging and validating this. So it's not easy to go, but we are getting to somewhere in the middle. Like for example, now we are trying to adjust the chunk time interval for the next chunk. So you can start with smaller chunks and merge them, and then grow to a big one. So here is an example. Like you have 1 billion rows per day. You aggregate the billion rows in one minute candlesticks, and then you have like this extra 360 billion rows, and then you can imagine that you can do some math and know like, hey, here is the residual growth of my database, but it's not growing crazy as your business. So this is another thing that you can think on doing this. And yeah, so this is like some sketches that's to build some ideas. And the rotation, the cool part of the rotation is this truncate mode. So truncate is the way that you can clean out a table that you like. If you want to delete everything, never use delete from. Just use truncate, because truncate will drop the system, the file system. Let's say that is linked to your database, and it's very cheap. And delete will mark the row by row to be removed, so you have the double of rows in your database. So like if you need, for example, let's say you have let's say 100 million rows that you add a new column in your database, right? Sometimes it's better to just create another table and backfill it, because it will just duplicate the 200 million rows, and then the vacuum would need to clean 100 million rows later. So it's always good to think about truncate, and it's also great to think about partition, because partition works well with these concepts together. And yeah, and yeah, this is a Postgres thing. So imagine that vacuum is like a worker that keeps going and cleaning your data as you update. You mark rows as outdated, and you need to keep vacuuming. And then the vet can also go and update the statistics, like, hey, I cleaned this dirt, and now I know how many rows I have, so it keeps updating it. But it has a cost, right? So, and then when you just drop the entire thing, you don't have any cost, right? And that's a good thing. I also think on indices, they also are like this. So just to recap here, hypertables partition your data, policies can serve to both compression and retention, and the continuous aggregates are hypertables that are like materialized views, but they are not really in the way that Postgres works. And the toolkit is just this extra extension that helps on statistics. And it's a very cool project if anyone is interested in Rust. This is a Rust project, and it also uses a project named the PGRX. Now it's a kind of Rails a framework for extensions in Postgres. It's a very cool bindings, and it generates extensions for you, like it generates all the scaffolding, so you can start playing in the playground and just like binding new functions. I built my extension in Rust, and I was able to write one method, and then I stuck, and then I couldn't make anything else. But I was building an extension named the PG Scraper. That was like a local GUI plus everything on SQL, and then you can fetch pages directly from the database. That was my toy project. So that's it, folks. Require TimescaleDB in our next project if you want. Also, if anyone can give me a GitHub star, my company will be very happy with my work here and say, well, this guy is doing something good. And if anyone has any questions, I'm open now. Thank you.
Usually, LSM trees are used for time series data storage. You implemented this over Postgres, but Postgres doesn't support LSM trees. So hyper tables are like SS tables of LSM tree.
I guess the concept used behind is inherited partitions. So I'm not sure if these inherited partitions use LSM trees behind the scenes or not, just to be honest. And yeah, so I don't know if I can answer this. I'm not familiar with the LSM tree concept. Can you explain a bit? Just
Just for time series, for example, influx DB.
Right. Yeah, I think we build a very dynamic thing. So we have like we say that it's for time series, but you can build your custom function that is the partition function, right? So you can build another dimension for your business, and you can also add extra dimensions. So you can like partition by, I don't know, like your tenants, for example. Right, you can have a tenant ID and your application, and then split the tables in this direction. But I don't think we use this concept because at least what I know internally is like Influx did it wrong. Like from the engineers, they always say it's like it was even a blog post from our CEO that they were talking about Influx as a company. They built 3 versions of Influx, and the 3 versions used a very different architecture from each other, and it was very hard to then you rely on it, right? So that's my only thing I know, and I never went deep into Influx to share it. So yeah, I hope we can talk more later. Anyone has any other questions?
Thank you. I came a bit late, so I don't know if this is solved, but do I need to create a table before I start injecting the data, or can I just start? Because I'm trying to solve my problem with custom metrics with TimescaleDB, but I don't want to create a table by hand. I want something more dynamic.
Yeah, so you can use your own tables. You can use your own data and just migrate your table to a hypertable. This is one thing. you can also build like an abstract model that just makes it dynamic. For example, we have prompt scale. It's not like a project today maintained by the company, but basically it's a backend of Prometheus based in timescale. So when you insert a new metric, it will insert a new table for you, right? So that's the point. I remember I have a repository named SQL snippets, and I have one example that does exactly it. And so if you want to check, I can share the link later. Yeah. Anyone else? Sorry. Throw the mic. Dangerous.
Okay, so my question is, this hypertable concept is kind of based on the thought of partitioning by range, which is included in Postgres, or this was like completely separate concept?
It's based on inherited partition. So inherited partitions, you make basically a check of the constraint, right? So when you create the partition, you can say like, well, I have data on this table, but this data comes from the beginning of the month until the end of the month. So if you go and check the constraints, you see exactly like timestamp between A and B.
So one more question, because I remember that like with partitioning in Postgres, the concurrent indexation is kind of a little deal, because you need to first apply index on the parent table, and then you have to iterate over child let's say tables, and it's kind of problematic. So you have to validate is this indexified or not. So have you solved this somehow, or you just iterate? How is it done in Postgres?
As far as I know, we patched it in somehow, right? So we have a version of create index that you can say with TimescaleDB async blah blah blah.
Okay.
That's like so. That's very cool. And in Postgres in general, we have this concept that you can include the keyword named with, and then you open parent and you put some configuration. So, for example, there is a configuration that's very nice that almost nobody uses. That it's named fill factor. So take a look at this if you have a time. Fill factor is like, imagine that you have too many updates. Like you need to keep updating your table all the time. So instead of completing the tables, you just you say like, well, I would like to keep this page only 70% filled because I know that the updates are coming, so it can use this extra buffer of storage to not create new page and scatter everything around. Yeah. Any other questions, folks? Anyone? Okay, guys, I will be around if anyone would like to stop. Thank you very much again.
Thank you.